Hello everyone. First of all, I want to thank you all for taking your time out of other two tracks and coming to the uh, my talk and attending this track. So, without wasting your time, we should get going with this. So, the topic which I am going to discuss today is Python, the role of Python in quantum key distribution, and most precisely in national security features. So first we will talk about quantum key distribution, what QKD is. So basically, quantum key distribution is the next generation of cryptography. After currently we use elliptical curve cryptography. Like if you use WhatsApp, you will see end-to-end encryption is listed there. But still, it's vulnerable nowadays because of the RSA and AES compliance, and also due to the rise of quantum computers. Because quantum computers take a maximum of 3 minutes to break a RSA code, even in two-factor compliances also. And AES codes are also broken by quantum computer, but it takes a little time. So for quantum immunity, or we can say post-quantum cryptography, we have the concept of quantum key distribution. It is also called photon cryptography. Why? Because the data which we have, we convert it, basically the data which we want to transfer over a channel, we use a particular channel called quantum channel. We convert the data into photonic distribution in certain angles like 45 degree, 90 degree, and all. There are 4 to 5 distribution for a single split of data, and then it passes through the quantum channel from Alice, the sender, to Bob, the receiver. Alice and Bob framework is applied in this case. So some of the protocols which are widely used in quantum key distribution are BB84, which I have discussed, which I mentioned right here. So BB84 protocol is the most widely used protocol. We used BB84 for military network security currently in some of the military installations in United States and also in India as a part of the Quantum Growth and Internet Alliance. Then we have E91 protocol. That's an old protocol which is susceptible to the quantum cryptography. And after that, we have QTIP. Basically, it's a library, it's a framework which is used to design circuits for quantum key distribution. Moving forward, I have mentioned few more libraries which we use for quantum key distribution. So first, we have Qiskit. Qiskit is basically a library, or we can say SDK, developed by IBM, which allows us to program quantum computers. So Qiskit is widely used nowadays. We also have Cirq, we also have Microsoft Quantum, but Qiskit is used, and it's widely used in security perspectives. And then we have QTIP, which I was discussing earlier. It's a toolbox kind of thing. It is used for measurement of qubits, measurement of different stages of qubits, and measurement of states. Like a qubit can exist in multiple states, not in binary, 0 or 1. It can exist in 00 state also, or 11 state also, or a combined state of 0 and 1 under any condition. Then we have OpenQKD. It's a noteworthy mention as it's represent initiatives and platform forcing the development of quantum key distribution technologies. And fourth one, which I was discussing earlier, Alice and Bob. That's the basic framework for communication between two quantum computers or in a quantum channel. Now we'll move to the implementation of quantum key distribution in Python. From basics, we have the environment setup. Like first, we have to install necessary Python libraries, like I discussed earlier, as Alice and Bob setup, and you should have Qiskit for circuit programming, or a QTIP for measuring the intensities of qubits and spectral density, etc. And then you have to initialize a quantum environment. You have to use Qiskit to create a quantum circuit. First of all, a simulator for your general binary machine, because getting a real quantum computer is I know. So you have to create a simulator which will initialize the qubits in poly distribution states. We have poly distribution states in which qubits are in general 0, 0 position, and then we have an Allen deviation curve which oversees the growth and then depreciation of data transmitted over qubit and data loss, validation loss from Alice to Bob. And the major part which comes into play while quantum key distribution is quantum entanglement, which also results in low latency. So quantum entanglement basically is a principle of quantum mechanics, the most famous principle, which states that spin can be communicated between 2 points, however apart they are. Like for example, maybe 2 photons are light years apart, but spin can be communicated. If one photon is flipped upside down, then the other one will replicate the same action, just in the opposite manner. So that entanglement principle which we are using in our quantum circuits for transmitting data between the 2 points, precisely Alice and Bob, and also in quantum synchronized clocks for lower latency over networks. Basically, it's used in the upcoming 6G frameworks for delivering low latency and high traffic with bandwidth. And then we have measurement and key generation. We have measurement protocols for both parties, Alice and Bob's, to entangle and check their qubit state, leading to the generation of a shared secret key. And that secret key cannot be accessed by anyone else outside the quantum channel. Even if some intruder tries to eavesdrop and tries to access the channel, the photons which will be reflecting from the channel to his system, when he will interpret, will give him false data, because of the angular transmission of photons. Like a photon is going on 45 degrees and 90 degrees. Like suppose 2-bit file is moving, and we are utilizing 2 qubits for the same. Then first one, let's suppose, is going in 45 degrees angle, and the second one is transmitting in 90-degree angle. And suddenly a eavesdropper, if in between attaches a converter, optical converter, and tries to read the data, he will get a false output because of the total internal reflection between the fiber optical channels. So that means it's unbreakable and unbreachable security. Then we should move to the most important aspect, what precise this talk was about, significance of QKD for national security, how it can affect the national security. As due to the rise of quantum computers, national security protocols and the general encryption protocols which government use nowadays are at a brink of breach. And most of the time we see in news that some or the other government data has been leaked by this source, that source. To prevent that, it's a way forward in national security. With enhanced encryption, quantum key distribution will provide unbreakable encryption, as I was talking about, because of the eavesdropping. Like currently also, we have multiple channels running for secure communication between governments. But still, those channels are breached sometimes. Like the case of Skypernet cable in USA. The CIA used to transmit its data to its embassies, but the channel was hijacked by some Chinese fellas, and of course I'm not targeting any community here. And the data was leaked. So the basic outcome is the data was leaked. So the thing is, it will provide unbreakable encryption also on the optical fiber channels also. So there is no breach between communication. Only the 2 parties which are involved in communication will be responsible. And also, like the current cases of data breach and privacy, which is over exaggerated nowadays. Like Facebook claims that we are giving end-to-end encryption, but we all know that it's not. They wait for your approval to sell data. So second, we have quantum safe communication. It's because of its nature, it's derived from the principles of quantum mechanics. The thing is, it is post-quantum cryptography. Because quantum breaking algorithms can work on RSA, AES, those type of encryption, but as it is derived from the same mechanism, so it's difficult to access the data from a quantum system. Because of the data is also floating in graphical format. It's not in steady. Sometimes the qubit can hold a value of 0, as I discussed. If you are, like in the example which I said, if the data is traveling at a 45-degree angle, then maybe while reaching the end, it can switch to some other angular. That's why synchronization and entanglement is required for, reading the data at the other end. If Alice is transmitting the data, then Bob needs to, I mean the receiver, which is a, used in telling the wordology, basically, basic wordology, Alice and Bob. Alice is the sender and Bob is the receiver. Right. So then we have cyber sovereignty assurance. Adopting QKD can enforce national cyber sovereignty, safeguarding against foreign surveillance and espionage of any kind. Cyber espionage has been a big issue nowadays from foreign military organizations and foreign intelligence organizations spying on other countries for, intelligence regarding, especially at time of elections, to topple governments. Then we have a new era, global security leadership. With global security leadership, we can have a whole new diaspora. People can share diaspora, governments can share tables to discuss the security and privacy among the citizens. I hope it happens. Highly unlikely, but still. So now we will go to the benefits of using quantum key distribution using Python. Why Python is necessary for this? There are many other languages. You can code a quantum computer in C++ also. But with C++, you will need 3-4 years to code a single program. So because of the Python simplicity, syntax simplicity, and the module import system, like you can use a particular module. If you want to program a circuit, quantum circuit, just import Qiskit and then design your circuit with how many layers will be there, how many type of superposition index, what will be there, what will be the H index, that you can program easily with Python. But if you will go for it in some other language, forget about it. So now efficiency and time saving also comes into play with the programming of quantum system. As quantum systems are believed to be the next generation of computers, the speed is the most important factor here. Like with QKD, quantum communications, quantum key distribution in quantum communications, we have the latency. Latency is the most important factor. Like with quantum key distribution, we have achieved picosecond latency. In the organization which I am doing currently internship in Dresden, Germany, we have achieved picosecond latency between TU Dresden and TU Munich, which are 500 kilometers apart. So we have picosecond latency is crucial for the upcoming architectures, like and also with zero breach. We tested for breach and all, and we got 0 as the light levels were different for each and every sector. No one was able to encapsulate, extract information. So it is also called photon cryptography. this quantum key distribution, which basically because it utilizes photons for the transmission. So moving to the some other applications of quantum key distribution, security, which I already talked about, and then in finance, fintech networks. Fintech networks are also on the breach of, always on the breach of, are always breached by, the hackers and all for information, especially the channels which claim itself to be the most secure are also hacked. Like back in India, the UPI system was hacked. Government system. Government claims it's the most secure system available on planet Earth, but still it was hacked, God knows how. So photon cryptography can help us with that. We can theoretically minimize, or we can say make the risk zero of loss of your financial information, and most probably the most important thing which we hold in our life, money. And then the other application is healthcare. Healthcare is the uprising and booming sector nowadays because of the street food and other things. They are earning a lot. So basically the point is patient data needs to be secured, because your medical history, your medical data can be used in some other way, in some other means by some God knows what organization where it is sold, your data for money. It can be utilized for multiple purposes, and eventually it can come back. Like if you have paid for something through your card or something at a hospital, with your history, the payment information can also be leaked out. That's a major concern. So that is the healthcare perspective of using quantum key distribution. And also one most important perspective is telesurgery. In telesurgery, we use QKD as a general rule for the robotic surgery architecture, which includes 6G networks. It is currently a matter under research. Basically, a doctor will be operating on a patient from a large distance, maybe 500 kilometers or 800 kilometers in general, as per the test has been done. So we have to achieve latency in microsecond, millisecond. Picosecond was achieved by us in our internship endeavor, but it was a 2-qubit system, so we can't expect it what will happen on a larger scale, but it was a very good beginning for us. So basically in healthcare, it will give a complete privacy, so that because a life may be in jeopardy if the network is hijacked by someone, the surgery network is hijacked. So before going to the thank you everyone slide, the last slide, so I would like to ask you all for Q&A. If you have any question. Yeah.
Thank you, Swastik, for that amazing talk. So for the Q&A, let's...
Congratulations, Swastik. It's a wonderful, that's a project right now, Iran. So with the emergence of AI, from predictive models to generative AI to conversational AI, if I am a hacker, why not use QSKIT and AI together and let AI do the hacking for me? Is that possible?
You can use that, but you have to access physically the quantum channel.
All right. So there's a physical security in IBM that I cannot access the actual, those processors. Yeah. But is that possible?
This is possible.
Outside our ethics.
Of course. Outside our ethics, it is possible, but I don't think IBM will give you access.
All right. No worries. Thank you, Swastik.
Thank you so much.
Okay, thank you for that question. So, do we still have any other question? We have, you can come to the center.
Hi. You see, quantum entanglement seems like a baffling concept for me because it's like two particles in vast distances. They can communicate instantly. Like it violates Einstein's theory of the relativity, I guess, right? But in your opinion, how do you see quantum computers actually being in the hands of consumers in their lifetimes? It's like fusion energy, where it's almost there, but it's not really.
As I said, it's currently under research, but there is a famous saying, the future is here, it is not evenly distributed. Einstein must have been, harmed by this quantum growth.
Thank you.
All right. Do you still have any other questions? Come to the center.
Hello. This is a bit more personal question. I hope you don't mind. I'm just curious, what does a regular week look like for you?
What was little bit?
For someone working in this industry, in this research, what does it like? What's the dynamic? How do you get around your day to day? Yeah, just curious. Are you more into the research or because I heard in the introduction you also do like reviews for publications. Yeah, so how do you balance all those things? Well, yeah.
Well,
Basically things you do on a regular basis. Yeah.
well, I'm not a quantum computer also. I'm a human. And all the tasks doesn't fall on me on the same time. There is, of course, a delay and leisure time in between. But yeah, I love learning about new things, and I block most of my work. Like if I did something, I write it in my Medium article or something, that kind of.
You're
And-
active in Medium.
Yeah.
Yeah.
And the most important thing, as I am single, so I have nothing. So being the brand ambassador of single community, I don't have anything else to do. That's why I spend most of my time on computer.
Sorry, is it more of do you work on a project basis? There's a specific topic you're working on for a few months at a time?
Yeah. That kind of. Currently, it's this same quantum key distribution in satellite communications between Earth and higher Earth orbit.
Okay, thank you.
Thank you.
Okay, thank you for that question.
Yes. Now the thank you everyone slide. You see, I was crying at that time. Please scan for having me in the. So once again, thank you everyone for having this.